Hello friends, last time we have defined normal subgroup and we have proved one lemma about normal subgroup. The definition of normal subgroup is a subgroup N is normal in G if for all G belongs to G, N belongs to N, the product Gn G inverse belongs to N. This is the definition of normal subgroup. And N is normal subgroup of G if this is the condition to be satisfied. For every G belongs to G, N belongs to N, G and G inverse belongs to N again. And the lemma we have proved is N is normal. N is normal in G if and only if we have G N G inverse is equal to N. This result we have seen last time. And now we consider the next result as lemma number 10. I have written the lemma statement here. The subgroup N of G is a normal subgroup of G if and only if every left coset of N in G is a right coset of N in G. That means left coset is equal to right coset of N in G, then N is normal. And the condition is if and only if. So therefore there will be two parts in the proof. First we shall suppose N is normal in G. Suppose N is normal in G. That means N is normal subgroup of G. And what we have to prove is every left coset of N is a right coset of N in G. And because N is normal in G, we use this lemma number 9. N is normal in G, we have G N G inverse equal to N. So therefore, for G belongs to G, we have G N G inverse is equal to N by lemma 9. This result we have proved. If it is normal, then that condition is again if and only if. N is normal in G if and only if G N G inverse is equal to N. And now what we shall do is post multiply both sides by G. And thus this gives G N G inverse into G is equal to N G. And the left side can be written as G N, we use associative law, G inverse G is equal to N G. And G inverse G is E. So therefore G N E is equal to N G. And again N E is same as N. E is identity element. And therefore G N is equal to N G. And this shows that this is a left coset G N. Coset we have studied earlier. Coset means every element of N is multiplied by, pre-multiplied by G, that is left coset. And this right coset means every element of N is multiplied, post multiplied by G. And thus this left coset is equal to right coset. That means every left coset of N in G is a right coset of N in G. So this shows that a left coset of N in G is a right coset. Right coset of N in G. And this proves the first part. We have made use of lemma number 9 here. Now we shall consider the converse part. That means assume every left coset of N in G is a right coset. And then prove N is normal. That we shall consider. Now second thing, we will suppose conversely, every left coset of n in G is a right coset. Right coset of n in G. This we shall assume. And now what we have to prove is n is normal in G. So because every left coset, we will consider G belongs to G. Let G belongs to G. And so Gn is a left coset. Then Gn, which is a left coset, is equal to some right coset of n in G. So this is by hypothesis or assumption. Now we have G belongs to G, and we will consider now E. Now E is equal to, we will have EG, or the G we shall consider, and that we will multiply by identity. G is equal to EG, and this belongs to NG. N is in N, and therefore E into G, this product is in NG, and this is in the right coset. We have written G as this is in a right coset, and or instead of considering right coset, first we shall consider left coset. So instead of writing EG, I shall write this as G. So because we can write both way, G is equal to EG or G is equal to G. E is identity, and now this belongs to Gn. So G is in left coset. So therefore this implies G must be in right coset, because every left coset is right coset. So now G is G belong to Gn is, then G is in some right coset of n, which is equal to Gn. Which is equal to this left coset. What we have written here is this G is in some right coset. Actually this G is in left coset, but left coset is equal to right coset, and we have written G is in some right coset of n, which is equal to Gn. But we can now write this G as EG. Now we will write G as EG. E is identity, and again this belongs to NG. So therefore G is in this right coset and G is in this left coset. But G cannot be in two right coset, because the right cosets are either exactly equal or they are distinct, and that means two distinct right cosets cannot contain the same element, and G cannot be in two distinct right cosets. So therefore we must have this Gn is equal to Ng. This G is in left coset Gn, but the left coset is equal to right coset, and again G is in this right coset, and therefore that must be the equal to left coset, and these two cosets must be equal. So therefore we must have Gn is equal to Ng. Now what we can multiply, post multiply by G inverse for this. So if you multiply this by G inverse, we will get this as G inverse. Post multiplying both sides by G inverse. And what is G inverse? That is NE and that is N. So therefore this is equal to NE and E is identity, therefore this is N. And thus what we have is G inverse is equal to N. And if we have G inverse is equal to N, then G is normal by lemma 9. So therefore here that is G inverse is equal to N. And this proves that N is normal in G. This proves N is normal in G. And thus the proof is complete. Both way we have proved. Assuming N is a normal subgroup of G, we have proved every left coset is equal to right coset. This is an important property of normal subgroup. Every left coset is equal to right coset. And assuming every left coset is equal to right coset, we have proved N is normal. So this is a strong condition, imply each other. And this completes the proof of lemma 10. Now we shall consider, before taking next lemma, now we shall write a note. Let A and D be two subsets of G. Then we have AB, or we define AB. AB by AB is equal to those elements of G, X belongs to G, such that X is equal to, in the product form, A into B, where A belongs to A, B belongs to B. So that is the meaning of AB. So similar to meaning of HA. How we have defined HA? HA we have defined the elements HA such that H belongs to H, A belongs to G here. And here AB is equal to the elements of the form A, small a into small b, where small a belongs to capital A and small b belongs to capital A. That is the meaning. When A is equal to B is equal to H, where H is subgroup of G, then what will be this AB will be H into H. This is H into H, and the element of this will be of the form we will consider H1 H2. This will be H1 H2, such that H1 belongs to H and H2 also belongs to H, or that means H1 H2 belongs to H only. Elements in the product form. H1 belongs to H, H2 belongs to H. So the elements of HH will be of this form. Now, by closure property, this H1 is in H, H2 is in H, H is subgroup, so therefore H1, H2 must also be in H, and therefore this is a subset of H. Also, H is equal to HE, and HE is an element of HH, because see, E belongs to H, H is subgroup, E belongs to H, and therefore HE is a subset of HH, and thus this is contained in HH, and thus what we have, HH subset of H and H is subset of HH, and thus H into H is again H because of only closure property. H1 belongs to H, H2 belongs to H, the product also belongs to H, and this is an element in this form. H1, the element of H is H1 and this is E is again in H, and therefore this product is a subset of H into H, and thus H into H is equal to H. So when H is subgroup, if N is subgroup, then N into N is also equal to N. So that is the property we have for this product. Now we shall consider lemma 10. Lemma 11. Lemma 10 we have proved. Now the next result is about the same normal subgroup. N is a normal subgroup of G if and only if product of two right cosets of N in G is again a right coset of N in G. So this is our next result. All these lemmas are important and they give the important property or condition for normal subgroup. Now this says that N is normal if and only if product of two right cosets of N in G is again a right coset of N in G. Now again there will be two parts, if part and only if part, or necessary part and sufficient part. First we assume N is normal in G. Suppose N is normal in G, and now we use this lemma. If N is normal in G, then every left coset of N in G is a right coset of N in G. Or further, we will consider let A, B, two elements in G, and since N is normal in G, we have a left coset is equal to right coset. That is AN, left coset of of N, left coset of N in G is equal to a right coset of N in G. That we consider the element as A. So we may have Gn is equal to Ng, Bn is equal to Nb, etc. So we have An is equal to N. And now we will consider the product of right coset, product of two right cosets, and the two right cosets we will consider as NaN. This is the product of two right cosets. Now what we have proved, this is also a right coset, and for this purpose what we shall write is N, and we write AN, B, associative law. These two are grouped together, associative law or associative property, and this is equal to N and this AN. Now you see, because it is normal, left coset is same as right coset, so this AN we shall replace by N into B, since AN is equal to N, left coset is equal to right coset, and further this is equal to N into N AB, associative law. But what is N into N? See, H into H is H, so N into N is N, so therefore this is NAB. and thus this is a right coset. NAB is a right coset. AB is an element in element in G. AB belongs to G, AB is in G, therefore NAB is a right coset of N in G. And this product of two right cosets is again a right coset. So therefore, product of two right coset is a right coset. Is again a right coset. And this proves first part of the lemma. Assuming N is normal, we have proved product of two right coset is again a right coset. Now the converse part we shall consider as assume the product of two right coset is again a right coset. Second part, conversely, suppose the product of two right cosets is again a right coset. Two right cosets of N is again a right coset of N in G. That we shall consider. Now let G belongs to G. Then NG is a right coset. Then NG is a right coset. And further, we have G inverse also. G inverse belongs to G. Therefore, N G inverse is a right coset. Now, the product of this right coset is again a right coset. Therefore, NG into NG inverse is again a right coset by hypothesis, because what we assumed is product of two right coset is a right coset. Right coset by hypothesis. Now we shall consider the element as E. E belongs to N, we have E is identity element, and identity element must be in subgroup N. So E belongs to N, and E we can write as EG into EG inverse. Now we should verify this. EG is G, EG inverse is G inverse, again G into G inverse is E. So therefore E can be written like this. And why we have written E like this? Because we want to say that this element EG belongs to the first right coset NG, and the second element EG inverse belongs to the second right coset NG inverse. So this belongs to NG inverse. Since we may write as E belongs to NG and E belongs to, so not E but EG. EG belongs to NG and EG inverse belongs to NG inverse. And therefore this composition or product belongs to NG inverse. But N can be written as N. E is itself a right coset. This is a right coset, and which is equal to N. And what this shows? See, E is in N, that is right coset, and E is in Ng into Ng inverse, that is also E belongs to these two right cosets. Thus, E belongs to Ne, and E belongs to Ng into Ng inverse. Therefore, now E is the identity element, and it cannot belong to two distinct right cosets. The element E cannot be in two distinct right cosets. Right cosets of N in G. This is a property of right coset. Right cosets are distinct or equal. So therefore, if an element, that means if this is G, set G, and if the right cosets will partition this set G into distinct cosets, right cosets. And if an element, if this is say Na, this will be Nb, this will be Nc, etc. And if an element is in this set, coset, it will not be in other. And or if we have Na will be equal to two right cosets, will be either equal or they are disjoint. That is the meaning. And here E is the element in N, and E is the element in Ng inverse. So therefore, these two right cosets, if this is the element E, then E is in this right coset, that is N, and therefore E must be this Ng inverse must be equal to N, only in the set. So single element cannot be in two distinct right cosets, and thus we must have this N must be equal to Ng inverse. Therefore, we must have instead I shall write here, also here, the word also here. Also, this is a right coset, and we'll write but here. But the element E. But the element E cannot be in two distinct right cosets of N in G, and therefore we must have this Ng inverse is equal to N. For G belongs to G. Now we will consider an element in this ellipse composition, Ng inverse. We will take the element in N as N1. With G we keep as it is. And another element of N as N. We may take N2 also, but we shall consider N, G inverse. And this belongs to N. So this is for all G belongs to G, N1 N belongs to N. And now see this further what we can do is pre-multiply by N1 inverse. So therefore this is N1 inverse, N1 into G, N G inverse. This will belong to N1 inverse N. We have considered the composition pre-multiplication by N1 inverse, because to eliminate this N1. And this is true for the same G belongs to G, N1 comma N belongs to N. And but you see, this is the identity. N1 inverse into N is identity, and thus only this remains, G inverse. So this implies G inverse belongs to, and again N1 inverse into N is same as N because of closure property. N1 is in N, and thus product of two elements in N is again in N. and this belongs to N. Since N1 inverse N is equal to N, as N1 is again in N, and G inverse belongs to N. So this is the definition of normal subgroup. If we have, this happens for all G belongs to G, N belongs to N, same condition. Now N1 is eliminated, and by definition of normal subgroup, this proves that, or this shows that N is normal. So this is the very definition of normal subgroup. So this shows that N is normal in G. And thus this proves the result. Assuming the product of two right coset is again a right coset, we have proved N is normal, and thus N is normal subgroup of G if and only product of two right coset is again a right coset. So this completes the proof. And thus up till now we have defined normal subgroup, and we have proved some important results of normal subgroup as lemma 9, 10 and 11. So you should try to understand these properties also. On the remaining part we will continue in next lecture. Thank you.